Good afternoon, guys. Yeah, there's quite a few of you here for something that's called Kubernetes something. It wasn't supposed to be called that. It was actually supposed to have a better name, but I decided to leave it as that because I thought it was a bit mysterious. Maybe it would actually intrigue some of you to come along. Basically, I'm going to be talking about Canonical's distribution of Kubernetes. I will be talking about running it on top of Openstack. This is actually something we do for a couple customers, and it's something we recommend. We can run Kubernetes on top of bare metal, and we also do run it on top of VMware a lot, but we actually prefer to run it on top of OpenStack, and there are good reasons to do that. A little bit about myself. So I'm a field engineer at Canonical. Basically, I'm a part consultant, part engineer, part pre-sale. So I sell products, go and deliver them, and then fix them when the customers find bugs. I work across EMEA, and I think my manager would be annoyed if I don't mention that we are hiring quite heavily for this particular role. Especially for OpenStack, we need lots more people for that all the time. So let's begin. So Kubernetes, it's a container coordination platform, right? So it's not an orchestration tool. So it's not like traditional kind of like things like ManageIQ, if you're familiar with that from Red Hat, or maybe some of the legacy VMware tools where you have like a workflow and it's like true, yes or true, true or false, sorry, and then it works through a workflow to deploy things, or perhaps like an ordering form or something like that. You know, it's basically a platform which delivers compute, network, and storage for containers. So by compute, we mean the Kubernetes essentially delivers and makes sure that we have somewhere to run our containers. It sets up the overlay network automatically for us. So we have a network that runs between all the worker nodes in the container to provide a network space for our containers. And we also deliver storage for our containers, and that's quite important because the storage is where all the persistence is. Basically, when you run Kubernetes, everything's ephemeral, right? So you really expect it to die. You don't want to do anything on those containers which should be long-lived or you expect to retain. You do all of that stuff on your persistent store, on your storage. So in a little bit more detail, so what exactly does it do? So lifecycle management, this is all around versioning of containers, rolling out new versions, rolling back if something's wrong. Every time you change something in Kubernetes, you can actually do an undo to that. So it records all of the stuff and the manipulations you do to Kubernetes, to the workloads on top. Scaling up and down, so we can do this automatically. We can scale up containers, we can scale down containers based on all kinds of metrics like CPU usage, memory usage, etc. And if you combine it with our tooling, you can also scale out your worker nodes as well. So these are the actual physical or virtual machines running the worker services. Service discovery, this is a funny one. This is about basically by using Kubernetes, you have this whole concept of service discovery where you basically map how to expose the underlying containers you have. And the idea is that you can actually discover the microservices that you have in your organization by using services. These are basically an exposure of the ports and of the containers that you're running to the outside world. Load balancing, so load balancing, we provide this as part of the cluster automatically. Different companies handle this in different ways. You can also integrate with external load balancers. F5 integration is something we see a lot, and it actually works really easily on the cluster. And finally, it's self-healing. So Kubernetes is able to work out and understand that if a worker node has died, and I've said, okay, I want to run this particular container 5 times, and some of our containers are on that dead machine, it will automatically move that load onto the other machines automatically for us. And that's quite nice, right? I think other architectures don't really do that very well, and I think that's one of the main benefits to using the system. So what I have here is a diagram, basically a high-level overview of our architecture. So we have the 3 main nodes in the system are the master, the worker, and the etcd. etcd is a highly available, basically clustered file, like distributed database, similar to Zookeeper, and this is basically the most critical part of the whole system. So if this dies, we basically lose everything, but we can actually use this particular component to basically deploy everything again, right? So if we take regular backups of this, we can rebuild the whole cluster. This stores everything. This just stores all the stuff about the pods I'm running, the versions, the deployments, all of the services, all the stuff I've just described. It's all stored in that database. The master component, well, that has the API and it runs the scheduler. It also runs the different controllers, so there's 4 of those. So there's a replication controller, which ensures that a certain pod is pod is basically a container or a set of containers is running a certain amount of times. I'll describe all these different terms in more detail later on. But there's also what's known as the node controller. So this is a particular service that runs to check if a node has died. It also runs the API, and we do everything through the API, right? So we have a command line tool, just like with Openstack, and we have a GUI, just like with Openstack, and they all run against the API that's running on those masters. The scheduler is what's basically ensuring, well, it basically decides where our workload should go, right? So we can say, Kubernetes, I want to run this container 5 times, or the scheduler decides which machines it should go on. You can actually write your own scheduler if you wish, and you can take real fine-grained control of this. So let's say you have a particular set of machines that have GPUs, for example. You can basically tell the scheduler to only deploy certain workloads on those specific machines. Or, for example, you have the concept of affinity and anti-affinity with pods, right? So let's say you have a database container and you have a web application container. You can, using the scheduler, you can basically ensure that those 2 pods will run on the same physical node for performance reasons. This is just one example. You may have some customer workload that can't run on one machine with another customer's workload, for example. You can do all this by manipulating the scheduler. So the worker, these are the nodes that do the main oomph in the cluster. You know, that they actually run the containers. They do all of the work for us. We ship 3 of these by default, but this is basically what you add to the cluster to add scale. They run the kubelet, so the kubelet is what schedules and sets up all of our containers based on the stuff that we've basically input and fed in through either the GUI or kubectl. The kubeproxy is what handles all of the overlay network with what's called a CNI plugin. CNI plugin is a container network interface plugin, so we have those for typical SDN vendors like Nuage and Contrail, etc. But there's also some open source ones which we ship by default. And these are also the nodes that run the Docker runtime, so they run the Docker daemon, and these are the ones that do most of the work for us, right? We also have an optional logging and monitoring stack that we ship on top, which is all based on a modified Elk stack, so it has Elasticsearch, Graylog, and it also uses Filebeat. We also have Prometheus and Grafana in there as well. I will be showing you those later on. So by default, this is what our default cluster contains. So all of those services I've just described, these are like the placement of those and how many units we have. So for etcd, we have 3 of them. This is for HA. It's just like Zookeeper, it runs all of them, and they're highly replicating to each other all the time. It's very network intensive. For the master, we run 2 nodes. So these are actually in active standby. They're both on, but they're in active standby mode. EasyRSA, we have 1 unit of this. It runs basically as a LXD container, which is one of our other technologies I'll talk about later. But this generates all of the SSL certificates for us, and it creates a self-signed CA. So by default, all of the services in the cluster are using SSL to talk to each other, so it's at least somewhat hardened, right? You can replace all this, and there's work going into this, so soon we'll be using Vault instead. This allows us to track when these certificates expire, easily replace them, etc. The kubeAPI load balancer, again, this is essentially what balances between the 2 masters. This is just a simple HA proxy or Nginx machine at the moment. But you can replace this with a traditional load balancer. You can set up an F5, for example, to point to both of these machines. The Kubernetes workers, again, these are the machines that do most of our work, so we run at least 3 of those. But customers usually run, up to 10, 50, 100, 200 of these, depending on how big their environment is. Again, the optional logging and monitoring stack, these are 2 machines. We have one specifically for performance monitoring, one for log monitoring specifically. And right at the bottom of this is quite important. So there is actually limitations, at least in Kubernetes right now, around how many pods and how many nodes you can have within a cluster. So on a worker, I can only run 110 pods, right? So this could actually be 110 containers max limit for each instance that I run of the Kubernetes worker. You can actually increase this limit. It's just an option on the command line. But if you do this, there is basically unexpected results and things could break, right? So the way that we increase this is either adding additional virtual machines or using LXD containers. There's a link there right at the bottom, and this explains these in more details. But every time they release a new version of Kubernetes, typically these limits increase. So here's a couple of the words I've just used. So a pod is basically the smallest unit of compute within the cluster. So this can be 1 or more containers, and this is typically what we're deploying all the time. A namespace, this is basically like a virtual cluster. Namespaces are used to segregate clusters. So if you have a big Kubernetes cluster and you want multiple people on your cluster, you typically have multiple namespaces. This could be different namespaces for different lines of business, different people, or different projects. A deployment is basically a way of describing, okay, I have these sets of pods and I want them to run this many times with these ports, using this particular volume for storage, etc. And these are what basically enforce the state. So based on deployments and what used to be called replica sets, Kubernetes will enforce a certain level of containers running. A service, so again, this is supposed to be like a microservice, but the way I see a service is, okay, I have these containers running, and this is how I want to expose them to the outside world. This is what describes the ports, inbound and outbound, and how I want to talk to those. Load balancing, so you have the concept of an ingress rule. When you define an ingress rule, what it does is automatically configures a load balancer within the cluster to create those rules. So any traffic that comes in based on those rules will be sent to the correct pods. So the last three terms are around storage. So you have something called a persistent volume claim, a persistent volume, and a storage class. So Kubernetes out of the box comes with a bunch of means of talking to storage. It's able to understand Ceph, for example, and Ceph is typically what we ship for customers because we use it a lot for OpenStack already. So you can define a storage class for Ceph. Within the storage class config, you would have a list of all the monitors within your Ceph cluster, and Kubernetes is able to talk to them automatically. So it has also a secret that is the key for talking to Ceph. And based on that storage class, and then based on the creation of PVCs, it automatically will create storage for you for your pods. And this is really powerful because it means you don't have to go around and create loads of NFS shares or create loads of block stores. You just create some storage classes based on the storage devices you have in your environment, and Kubernetes can automatically satisfy those requirements for storage for you. So I just put at the bottom there, all of this stuff is YAML. So every time I create one of these, it's just a whole bunch of YAML that I input to the cluster. All of this can be edited using the command line tool and just instantly saved, and also exported in the same way. It's really powerful, and in a bit I'll show you how to do some of that stuff. So it's worth covering some of the different platforms that we ship on. OpenStack is one of our main ones. VMware is that we see this quite often as well. We also support ARM, and we've also done Kubernetes on top of IBM mainframes. We've done it on top of System Z as well, which is a bit odd, but yeah. But we also support all of the public, the main public cloud vendors, and we also support on bare metal too. We've also been doing some work around ARM, so we actually have ARM support now for Kubernetes. There's a cloud vendor out there called Packet, and you can actually rent 96 core servers from them for I think 50 cents an hour. So it's really quite interesting that space, and especially how they compete with Intel now. So yeah, okay. So we're going to move on to some of our partners and stuff. So what about management in the cluster, right? So when we deploy these clusters, they just ship with the open source Kubernetes dashboard, and this itself it can do most of the stuff you need to just run a cluster individually. But if you're in a business and you need multi-tenancy and you need a way to, like a single management plane for multiple clusters, it really doesn't do very well. So we partner with Rancher. Rancher ships a very nice product for managing multiple clusters. So you can have one instance of Rancher deployed on your internal premise, and then you can actually connect that to multiple clusters in different public clouds, for example. And I can give you a quick demo of what that looks like. So I already have a Rancher set up on a cluster on public cloud. So this has actually got multiple clusters attached to it, and I can literally go in and I can deploy a workload. Let's call it something silly. Okay, I want to run this container 5 times. Hit launch. So what this is going to do now is going to pull this container that I've got from Docker Hub by default. Of course, you can define your own registry and link this up to your own registry as well. As soon as that's done, I can then jump onto the cluster. Actually, I'll open a new tab. So kubectl is that command line tool that I mentioned, and it should, or namespaces, you should see, yeah, it's created a whole bunch of containers in the last 40 seconds. So those are the 5 containers that I've just specified. You can do all this stuff on the command line tool as well. But this gives you a graphical interface, and it also does other things as well. So it brings the concept of a project to Kubernetes. There's no concept of a project. It gives you somewhat of multi-tenancy, because it could actually integrate with that Active Directory, and it sits in front of the existing components on top of Kubernetes. So you can get like your kubectl config file for the command line tool is all generated by Rancher and managed by Rancher. So it provides this management interface in front, right? So now I've deployed those pods. What I can do is just add specify a host name. So I'm going to use this zip.io service, which is quite used a lot for demos. This is just a free service that it just returns I records based on the IP address that you put in front of it. So what I do then is I choose a workload. So I'm going to choose cat. I'm going to put 80. Now this should go to this new tab. There we go. Simple, right? So all of that stuff I've just done there, you can do this on the command line. You can do this through the open source dashboard, right? It's really easy, and it's much, much easier, I think, in Rancher to do this. And Rancher, once you really get into it, you have to define things like pod security policies, network policies, all of this stuff to add real security to your cluster. And writing that stuff manually is a little bit tricky and painful at times, and Rancher really makes a good use of that. So for example, one thing I can do down here in the advanced options is I can actually set, for example, memory reservation or CPU reservation around, and I can put some constraints around this. You can see here they've also got NVIDIA GPU reservations. In the future, they're going to add the ability to do this carving up of GPUs that NVIDIA's been working on, for example. So if you have like a machine learning workload, you can carve up a GPU that way. And with our distribution of Openstack on top, we can actually do pass-through of GPUs all the way through up to the VMs and then up to Kubernetes. So I mean, what I can do now, for example, is I can change the scale. I can also change the version. And as soon as I change the version and save, it will basically redeploy it. And this is all totally configurable as well. So what I've just done there is just a blanket rollout of a new version. But what you can actually do is configure how the new version is rolled out. So you can say, okay, maybe I want to keep 50% on the old version, 50% on the new version, or maybe I want to roll them out gradually just in case anything bad happens. So you can do things like A/B testing, all of this stuff. It's totally configurable. I wonder why one is not running. Maybe there's too much running on my cluster, but it should. Maybe not. I'll take a look in a second. Maybe it's to do with the version. Maybe both version 1 and version 2 are actually the same container right now. Let's get back to the slides. So that's Rancher, right? So Rancher is just a nice interface on top. So what about storage? So I mentioned PVs, PVC, and storage classes. By default, we ship with Ceph. We've just recently added the ability to do encryption at rest out of the box with Ceph to meet GDPR requirements. But another quite common one we see is NetApp. So we can do NetApp Trident. This is like ONTAP, Centricity, those kind of devices, all out of the box. And it integrates really nicely. So basically, at some point, you need to store stuff in your containers. It may be a database. It may be some other, maybe even temporary volumes, right? So if you're doing something like a broker, like Kafka or something, you need some temporary store to use for your data. So you'll need persistent volumes at some point, right? You can reuse disk space on your local machine. You could use, or just like a traditional NFS or iSCSI. But when you have some nice integration, it just means that you can spin up all of this stuff automatically for you. So what I can show, I actually have Ceph already on this cluster. So you can see there's ONTAP, and there's also RBD, which is for Ceph. So I can just literally do edit storage class default. This is the definition of a storage class. So like I said, everything is defined in YAML. And what you can see there is there's a line with the monitor. So this is basically all the config that is needed to run Ceph on the cluster. All I need to do is define a storage class. I need to put in this line with the mons, and you can see it's also it has a secret. So There's another built-in construct within Kubernetes called a secret, and it's just an encrypted string, and this is just the API key that it uses to interact with Ceph. And this is all Kubernetes needs to understand that, okay, I have Ceph available, I can use it for storage. So once I have that defined, so for example, let's have a look at one of these. Example, I think I created one of these. Yeah. Whoops. So this is a persistence volume claim at PVC that I described earlier. So when I create this, basically what it will do is tell Kubernetes that I have a claim for 2 gigs. I basically have some workload that needs 2 gigs. Give it to me. And what it will do is basically do it for you. So if I do PVC, so you can see that there's a couple that are already bound. So all I need to do is kubectl apply-f, example PVC, YAML, and it goes and creates it for me. And you should see that it's already picked it up and bound it already, right? So it's already solved this requirement. It should have created a PVC, so one of those should be 15 seconds. So right at the bottom there it says 15 seconds, so it's literally just said, okay, Kubernetes has picked up this PVC and it's gone, okay, some workload needs some 2 gig of storage, and it's just created it for me automatically on Ceph. And this is quite nice, right? Because if you have some workload that needs storage, you can just literally combine everything together. So I've got, this is a particular big construction of YAML, right? This is different constructs that it's putting together to deploy one particular workload. So you can see how I have the claims at the top. This is for something called Minia, which is an S3 on-premise storage solution. You can see here it's got a claim at the top. It then has a deployment. This describes the containers and the ports that are open on those containers. And you can see here it's referencing the PVC inside it. So it says there it has a claim and a claim name. And based on all this stuff, it will basically deploy the containers, deploy the storage, and set everything up for me. And then right at the bottom, it has the ingress rule. So this is what all of those things I described all put together to deploy something. So networking, we ship with Flannel, Canonical, CNI plugins by default. These they basically give you different benefits, right? So Flannel is a simple layer 3 overlay network. This is the default one that we ship, but we usually recommend Canal, which is a combination of Canonical and Flannel. One brings network policies and the ability to constrain traffic, whereas one is just the layer 3. And you can also do things like I believe BGP between the overlay network that runs across the containers and the outside world and that kind of thing to improve performance. You can also do VXLAN with these. But there's all plugins that come from all the traditional vendors, right? Like Contrail is one, Weave is a new one that we've seen, and obviously Big Switch as well. And basically with our tools, you just modify the bundle and you just change the plugin, and when you deploy Kubernetes, it's easy to pick and choose whichever you want. So I did pull a container from Docker Hub when I just did that, but we also support a couple other registries, and there's many that you can use, right? We partner with JFrog for Artifactory, which is used a lot in the enterprise world, but you can also use Nexus. On this cluster, I actually have Sonatype Nexus deployed. But basically, a container registry is just like a regular repo, right? You just push containers in and version control them, you label them, and if you've used Docker before, it's quite straightforward. So I've been working on a demo, but I admittedly have not totally finished it, so I'll show it. I won't show it, but I'll basically describe what I've been up to and what we've been up to as Canonical around machine learning. So we have a very good partnership with NVIDIA, and we also have a very good partnership with Google. And we've been working with them to basically bring TensorFlow to our cluster with ease, right? So we want to be able to deploy what's known as Kubeflow, which is basically, it brings batch jobs of AI to the cluster, right? So if you're familiar with the Hadoop world, you have Spark, and Spark can run batch jobs for big data, right? But with this, you can do the same, but you can do it for AI. So one thing I've been working on in the background for the last few days is basically a game, and what it does is every time the enemy opposition makes a move or whatever, it uses this. So it basically runs a batch job to understand where the next move should be and returns it, right? This is quite a powerful tool. I think it's actually used for Google Translate. So every time you do a translation on Google, they're actually sending it and doing a TensorFlow job every time you do that. we've been working with like car manufacturers and that kind of thing to do lots of stuff around this, especially around the IoT space and things. So where does Kubernetes fit in with OpenStack? So we as Canonical, we see them as a good fit together. You know, we have this recommendation of using a hypervisor with Kubernetes because otherwise you're just reusing the underlying kernel, right? And this isn't great for multi-tenancy. This isn't great depending on the workloads you're running. You may have a malicious exploited container which could then exploit others at the kernel level. So what we do is you combine this with a hypervisor. OpenStack has been around for a very long time. We see this as a very tried and tested solution. So it has a very wide ecosystem. If there's something we can't solve with Kubernetes, most likely we can solve it with OpenStack. If it's billing or logging or metrics or whatever, usually we can solve it. It also brings the strong multi-tenant model. So I'm not just talking about the hypervisor, but also at the network level. So SDN and NFV, for example, and you have this network segmentation, but also at the hypervisor level as well. This really adds to the benefit, like it really pairs well with Kubernetes because Kubernetes at the moment doesn't have a great model for this. The one at the bottom, we've actually seen quite a few big telcos out in the States ask about this. So some customers want to run the OpenStack services within Kubernetes because they believe the way that it rolls out services gives you the ability to increase the version and roll it back and everything is really quite powerful. This hasn't become widestream yet. We haven't started to do this on scale, but we've been thinking about it. I think it could work, but it is a bit odd. I will give it that. So maybe we'll see that some more in the future. So yeah, there is many issues around Kubernetes, like with the capacity management, all that kind of stuff. Authentication is another big one. There's no real authentication mechanism out of the box with Kubernetes. It's all token-based. It's all really exploitable. So you have to add something on top, which gives you AD or LDAP, etc. So one thing that was announced basically at ODS is something called Microkates. Microkates is our competitor kind of thing to Minikube. Basically, the idea is you can give yourself a Kubernetes development environment in one command. So what I'm going to do is jump over to a machine that I have freshly installed. So it has the snap client already installed. So I'm just going to do sudo snap install microkates -- classic beta. Yes. So snaps, if you're not familiar with Ubuntu, so snaps is a kind of a new package format that we came up with, and it's containerized and it's isolated and it allows you to do automatic upgrades and roll back and forth. The idea, it came out of the mobile world when we used to be involved with mobile phones, and we basically had a really hard, we worked out how hard it is to ship software to phones. And it's a nice tool, so all of the services for our Kubernetes cluster actually ship as snap. So the updating between the minor versions of all the services like the etcd, the worker, etc., it's all done automatically. Major version upgrades are not automatic, but that's, yeah, maybe a future thing. So I have it installed. So now I can just do microkates enable DNS. So what this is going to do is start up the DNS servers on the cluster. There is actually a I had this issue earlier. There's a basically automatic DNS resolution within the cluster. I'm trying to think what this was now. Yeah, I do have it running locally, so I could do that. Yeah. So basically, when you install it, you have to do this. So what this does is it spins up the internal DNS. So it's basically a pod that runs on top that does the internal DNS resolution. Because within the cluster there is automatically DNS resolution and hosts and entries created for each of the different machines that run all the different pods, basically. So if you have a cluster of different pods, they can talk to each other, basically. I'm going to do dashboard. So doing that command enables the Kubernetes dashboard, the standard one. And then from there, oh no! Yeah, another error. Give it a second. This is not good. Now it works. All right, okay. So I've gone back over to the other machine and now it's working. I think it's to do with the fact that I just installed the snap and it takes a little while to sort itself out, start its services. Yeah, there you go. Awesome. So I have the command line tool all out of the box with this. So I can do run, cats, whatever, image. V1. And then replicas, say 3. Looks good to me. So what this will do is automatically create a deployment. Deployment. Whoops. And also the pods, because the deployment describes how many pods I want to run. So it's pulling the container in now. This will take a little while. It also should be running the dashboard. So I think I'm running this particular one on 8010. Yeah. So this is the one I've just spun up on Amazon. So I've just created a fresh machine in order to do this. So you can see it's created all that stuff. So this is the open source dashboard. This is the one that ships by default with the cluster. And this allows you to do almost everything you can do within Rancher apart from the AD integration and that kind of thing. You can literally edit things in YAML through this GUI. You can check what's running. There's some basic stats around the cluster, etc. So for those of you who are not familiar with Ubuntu or the kind of Ubuntu ecosystem, here's just a quick breakdown of all of our different tools. So we have Juju. Juju is essentially similar, like it's basically a mix, to me it's a mix of Terraform, Ansible, and Puppet. So it can not only understand the APIs for interacting with, say, OpenStack or AWS or Azure, but it can also deploy the solution using things like just with regular SSH, like Ansible. It can deploy things like we use it to deploy OpenStack. We also use it to deploy Kubernetes. Maz is a tool for provisioning bare metal machines. We use this to provision Ubuntu images, Ubuntu machines, but also we can do CentOS and also Windows. We can do other operating systems too. We combine these two tools together to deploy OpenStack. LXD is a container platform that we have, well, a kind of runtime that we have that's used to model essentially virtual machines. So we use this to create containers which are like virtual machines, more like pets than cattle, right? And snaps I've just described, and yeah, we also have our own distributions of OpenStack and Kubernetes, as I've been explaining. So deploying CDK is actually very simple. So it's just a little bit similar to what I just did, but not quite. So I already have Juju set up on this machine, so I actually have a cluster here, but all I need to do to deploy Kubernetes is do a Juju bootstrap, so I can do AWS, US1. So what you would do is you would actually, if you were deploying on OpenStack, you could add the OpenStack as a cloud provider within Juju. So I can just pick a region. What this will do is create the controller. And when the controller is done, we can just deploy the model. This will take a little while. So what I'll do is I'll go back to the other one I created. So I have created some containers. This is on the other machine that's running microcates. And then I can expose them. I should have a nice big long command. So then I can do something like so this was the services I was talking about, so I can do something like this. Port 80. We can see that we should be able to see that the workload, the same workload that I had before is running there, right? So I've deployed that on my local machine. If you're running this on your local machine for development, you can do exactly the same thing, and you would be able to hit this in a browser. And if I go back to the other cluster very, very quickly, okay, that will take a little while. once that's spun up, I can show how that works. So I'm near the end now, but this just describes basically the steps required to deploy on top of OpenStack. There's two ways to do it, right? There's the good way and the bad way. So the good way, you basically set up what's called the cloud.conf. So Kubernetes is actually able to understand and utilize the OpenStack APIs natively in order to spin up its storage, but also spin up its additional worker nodes as required based on the auto-scaling. And this is more involved than deploying on something like VMware, etc. You just need to do a bit of additional configuration around the kubelet, but it's nice that it's able to interact just like on AWS with the north-south APIs. It can do exactly the same thing. The bad way is where you deploy a whole load of virtual machines yourself, give them all the DNS entries and the IP addresses they need, and then you can basically do a manual bootstrap. And there's a couple of examples here on how to do that. It's not very nice. I'd much more prefer to do it this way and suggest doing it this way. So yeah, that's basically it. Is there any questions? Please feel free to ask anything about Kubernetes. Nobody? So I did just deploy. So this is just created on AWS the controller node. So what I can do now is you deploy Canonical. If I can spell Kubernetes. What this will do is automatically pull down what we call the bundle file. The bundle file is basically like a big playbook. It describes all the different, we call them charms. They're basically like a little bit like Ansible roles or Puppet modules for each of the different services. It describes the versions of those, all of the different relationships between them all, and just we'll basically deploy the whole Kubernetes cluster for us in basically 2 commands on AWS. It's a little bit similar on OpenStack, but there is a little bit more you have to do. But yeah, that's basically how you deploy the solution. And then after it's deployed, you can just do a Juju SCP. And what Juju SCP will do is you copy the kubectl file, the config file that we need, over to your local machine, so then you can interact with kubectl to spin up containers on top of the cluster. So yeah, is there any questions? Otherwise, I guess we can finish. That's basically all I had to present. So.
Okay. So, is there any questions? So first of all, thank you very much for having a lot of different demos here.
Yeah, I wasn't too sure exactly what I was going to cover. It was just very broad. I wasn't too sure on the audience or what their knowledge of Kubernetes would be. And I wanted to deploy on top of OpenStack, but it's getting an OpenStack cluster within a few days is a little bit tricky sometimes. So. Yeah. We do have one that's running upstairs, actually, that I was hoping to use, but yeah, it's...
For sure. And especially doing this on a stage is even worse as a demo. So we would say that demo gods are always there and try to, screw you up. So, I would ask the audience for the last time, do you have any questions regarding Kubernetes on OpenStack on Ubuntu? No? Okay. Then thank you very much for the talk. It was very exciting.